So we begin our lecture on sum of convergent sequences and their products, and we'll see how this convergence has interaction with the binary operations that are present in the for the real numbers like addition, multiplication, and their inverse operations as subtraction and division. Everything will be summed up in the following theorem, which states that suppose that we have sequences. Yeah, let us take three sequences. Only two sequences would be better. The convergent sequences, such that we have this sequence xn converging to a limit x and sequence yn converging to y. Then we have the following. We remember that the sum of the sequence is defined to be a sequence obtained by taking the sum of the corresponding terms of the sequence. Then this sum is a sequence which converges to the sum of the limit of these two sequences, that is x plus y. And for minus also the same holds. Better to write it here only. And second, the product of sequences, as we know, it is defined as the sequence obtained by taking the product of the corresponding terms of the two sequences. This is a new sequence, and this sequence converges to the product of the terms of the product of the limits of the two sequences which are being multiplied. And finally, we have the quotient of the sequences, and this is defined as a sequence in which we take the quotient of the corresponding term of the sequences provided denominator is non-zero, and this sequence converges to the quotient of the limits, but provided here y needs to be non-zero, and also at those points where this nth term of a sequence y vanishes, we don't consider that, we have to skip that part. And but for that we have to assume that at most this y has finitely many terms which are zero, otherwise it has to be every term to be non-zero. So let us write its proof, and we will begin with this first one. I will consider the case where we are considering the sum of the two sequences, as the difference of two sequences will follow on the similar lines. So let us try to prove that the sum of two sequences converges to the sum of the limits, and let us take some number positive epsilon, then applying the definition of convergence on the convergence of the sequence x and y both. So for them we will get two, there exist numbers n naught, this will also depend upon epsilon, and let it be n1, and I will get another number n2, this will also depend upon epsilon greater than 0, such that I will have this convergence of xn, means the distance of x and nth term of x from x will be less than from number epsilon, but here I will stick to epsilon half for every n greater than or equal to n1 epsilon. And likewise, in the case of the convergence of the sequence y, the distance of the nth term of the y from y is less than epsilon half for every n greater than or equal to n2 epsilon. Let me mark these equations as 1 and this inequality as 2. And let us note the following observation. See, if I choose a number n which is bigger than both from n1 and n2, then both the inequalities first and second hold for that particular choice of n also. That is to say that if I take n to be a number which is maximum of these two natural numbers n1 and n2 epsilon, and clearly it will also be a number which depends on the epsilon, and clearly it will be also greater than 0, then we see that for any natural number n greater than or equal to n, uh, inequality 1 and 2 also hold. Both these inequalities are true for it. So what we want to know, we want to show that the distance of the nth term of the sum of the sequence, this is the nth term uh, from the sum of the limits, that is x plus y. This distance needs to be brought to be down to be less than epsilon for particular choice for all those n of greater than or equal to some natural number n. And here this natural number n will be this n epsilon, which is maximum of these two, n1 and n2. But here we just require in the intermediate step, I can write this as xn minus x plus yn minus y. And if I apply the triangle's inequality, by triangle's inequality, I will get less than or equal to xn minus x plus yn minus y. And since I have chosen n to be bigger than or equal to n epsilon, and obviously that means that this is bigger than or equal to n1 as well as n2, and so the inequalities first and second can be employed here. And if the application of these inequality 1 and 2 gives us that the first term in this sum, that is the distance of xn from x, is less than epsilon half plus y, distance of yn from y is also epsilon by half, and this is equal to epsilon. And see, we have this thing. We begin with a positive number epsilon greater than 0. Then we have been able to find a natural number n, which clearly depends upon the epsilon, such that whenever you have n greater than or equal to n epsilon, then the distance of the terms of the sum of the sequence from the sum of the limits, that is x plus y, is less than epsilon. And epsilon was an arbitrary number, and hence by following the definition of the convergence, it follows that this sequence xn plus yn is a convergent sequence and it converges to x plus y. So this is this way this proves first the sum part, and likewise on the similar lines, indeed replacing plus by minus, you will get that xn minus y also converges to x minus y. So in this particular case, I have that this proves first. So now let's look at the second part. Let's look for the second part, and let us first look at this thing. Since xn sequence and yn both sequences are bounded, hence there, by using the definition of the boundedness of the sequences, there exist numbers, let us say m1, and another number I can find m2, such that by using the definition of boundedness of a sequence, I'll have that mod of xn is less than m1 for each n, and as so yn will be bounded because convergent sequences are bounded. And why am I taking these to be bounded? Because they are convergent sequence, and convergent sequence is always a bounded sequence. M2 for all n greater than or equal to not integrate, this will be true for every n indeed. So let us take m to be maximum of this m1 and m2, then c, then you can see that the maximum, then you can see that mod of xn will be less than m for all n, and likewise this modulus of yn is also less than m for every n. So this m works for everything. That means you take any m larger than m1 and m2, that will be a bound of these sequences as well. Okay, now we require this to this the following trick, and now I have to establish that the sequence product of these sequences converges to the product of the limits of the corresponding sequences xy. What I'm going to do here, I'm going to give you something here, and I will apply triangle inequality. Let me write it as xn y. I'm going to add the same number, and let us see how this addition and subtraction, this balancing act helps us to. Let me get xn out of this sequence yn, this number. I will get yn minus y, and from the last two terms I can take out y. I will get xn minus x into y. So I'm going to employ now the triangle inequality on these two terms, and that will give me mod of xn yn minus y plus mod of xn minus x into y. But in the next step, I can write it to be mod of xn, since modulus of the product of numbers is the product of the modulus of the numbers. And so that with this help, I get this thing, and this is equal to mod of y into xn minus x. So I'm going to put here a note that if we replace m, which was the bound of these two sequences, by the maximum of mod maximum of m and mod y, this can be done, because this will be again a bound, this will be again a bound for both the sequences x and y. As I said already, that if you have a bound, if you take any number which is larger than that particular number, that will also be a bound. So I'm taking a number which is larger than this, and let that number again be renamed as a m. Then from this inequality, let me call this inequality as star. Then from this inequality star, what I will have this, let us first write this left hand side, and this will be less than or equal to, since mod of xn is less than or equal to m, and then it is yn minus y. As I have taken m to be maximum of m and mod y, so it is bigger than this y also. So I can take this m and I can take this mod of y to be less than or equal to m also, so that this m can be taken out as a common number. So I am left with these two terms inside this bracket now. And let me take this inequality as a double star. Now we have to go back to the convergence of these two sequences xn and yn, and for that I have to apply that inequality on yn and that convergence of yn and xn. So let us begin with some number, as we have to begin with some arbitrary number to establish the convergence of the product of the sequence, and let that epsilon be greater than 0. Then by using the convergence of xn and yn, again I will get some numbers, natural numbers indeed, or positive integers you call them also. There exist numbers n1 depending upon epsilon, and I will get another number n2 depending upon epsilon, such that I will have this mode of xn minus x less than epsilon times m by 2 for every n greater than or equal to n1, and similarly convergence of yn implies that the distance of the nth term yn from y is less than epsilon times m upon 2. I can take epsilon, this number on the right hand side of this inequality according to the convenience that we need. And again, as noted in the previous, in the case of the convergence of sum of sequences, note that both the above inequalities hold for any number which is greater than the maximum of these two numbers. Both the inequalities above are true for any n which is greater than or equal to the maximum of these two numbers, n1 and n2, and let that maximum be denoted by n. And clearly this n is also dependent on epsilon now. Thus, for n greater than or equal to this capital N, we have this number xn minus x plus yn minus y. This will be less than m times epsilon by 2 plus m times epsilon by 2. This is equal to nothing but m times epsilon. And thus from this inequality here from double star, we have this estimate for this number which is within the brackets, and this estimate is what? This is epsilon upon 2m. So we need a bit of change here. What change I'm going to get here? I'm going to replace this m, and I'm going to keep this. I'm going to put this m in the denominator. That will also work because m is a positive number. Because I need to cancel the m in the equation star. So I will have this as, again, I have to replace it. So I will get this number outside and in the denominator. So I will be left with epsilon upon m. And I have this epsilon upon m here, and thus from this equation double star, the m and m will be cancelled out, and what I will be left with, thus from equation double star, I have this distance of the product of the terms of the sequences from the product of the limits x and y will be less than m times epsilon upon m whenever you take n to be number which is greater than or equal to n, and this is nothing but equals to epsilon, and this is nothing but just the definition of the convergence of a sequence here, since this epsilon was an arbitrary number, and hence it establishes that this sequence, which is product of the sequences, converges to the product of the limits. You can also write this as this by using this limit notation. There is no harm in this. This also gives a good feel to write xy, but note that this x is a limit of the sequence xn. You may replace it with this notation, and this y is a limit of the sequence yn. So you may write it as. So this gives that this limiting operation in the sequence of convergent sequences can be applied point-wise also in case of product and in case of sum also. So this is for sum, and now finally let's look at the third part where we have to talk about this number, what you say, the reciprocal of a sequence first, then we will say that the quotient of sequences is also convergent sequences is also a convergent sequence. So first we suppose that for the quotient each term of this sequence is non-zero, and y is also non-zero. otherwise we cannot define the quotient. And first, so we suppose that, and we first would like to establish that the reciprocal of this sequence converges to the reciprocal of its limit. And because then from second that we just proved the product of sequences, from second xn yn can be considered as a product xn into y up 1 upon yn, and from second it will be converging to x into 1 upon y, that is equal to x upon y. And that is why we will only prove in this case the reciprocal of a sequence converges to the reciprocal of the limit. Okay, let us take, now we have assumed this y to be non-zero, so its modulus is positive number, and let us take a to be a number which is 1/2 of this mod y, and then let us apply this convergence definition to this a being an epsilon, and see then what happens. Then by this definition of convergence, by this given condition to us that the sequence converges to y, I can choose a number. There is a number, some, let it say be n1, which depends upon obviously a, let's not express it. And there is a number this such that whenever you take a number which is larger than this n1, what I will have this yn minus y to be less than this number a instead of epsilon. That is to say that minus a is less than yn minus y, and this is less than a. Or what we can also write, we can also write it in some different way, and there will be a very problem in writing this. And so by the way, we have this thing, we want to show this yn being a bounded sequence, not yn being a bounded. I need to show that this reciprocal of yn is a number which is bounded by some number, but for the time being, let it be like something like this.